Okay, so let's start. In the last class, we looked at a couple of inequalities, a few simple tail bounds that we could derive for first for non-negative random variables and then for general random variables. Right, so we started off with this Markov's inequality, which says that if x is a non-negative random variable with finite mean, then the probability that x is greater than or equal to some positive constant t is upper bounded by the ratio of the mean to t. Right, and this is okay, not very tight, as we will see. But at the same time, it helps us derive much more stronger bounds, right? And to see why that was the case, we immediately saw another inequality, Chebyshev inequality, which holds for more general random variables. But then we had this additional constraint that we had the variance has to be finite. And ultimately, the bound is tied to the variance. The larger the variance of the random variable is, the looser your bound will be. Right, so we showed that the probability that x deviates from the mean by an amount greater than t can be upper bounded by sigma square divided by t square. Okay, and this holds for any t which is greater than 0. Okay, we saw proof of this, and we immediately see why this is better than Markov's inequality in some sense. The main reason is that ultimately we expect that the larger t is, the smaller the bound on the right hand side should be. So the question is how the right hand side varies as a function of t. In this case, in Markov's inequality, the right hand side varies as 1 over t. Correct? But on the other hand, Chebyshev inequality, for the same amount of deviation, we see that the right hand side decays as 1 over t square. Right, which is smaller than what we get using Markov's inequality in general. Of course, it doesn't hold for all ranges of t, and the main reason is that this also depends on sigma square. So if sigma square is large, then the right hand side will be pretty large. And of course, this makes sense. Chebyshev's inequality is useful only when t square is greater than sigma square. Right, otherwise the right hand side is some quantity which is greater than or equal to 1, so we just get a trivial bound. Correct. So in order to use Markov's inequality for the right hand side to give you something non-trivial, you need t to be greater than mu. But on the other hand, if you want the same thing using Chebyshev inequality, which is slightly different, we're looking at the probability that x minus mu mod of this is greater than t. So in this case, we want t to be at least as large as sigma square. So all of this is good if sigma square is small. Correct? As we saw in the case of IID random variables, when we have a sequence of random variables and we wanted to find the deviation from the mean of the empirical average, the variance of this particular random variable is sigma square by n. So for large n, the variance is really, really small. Correct? So that gives us a nice bound. So it's sigma square by n epsilon square, which tends to 0 as n tends to infinity. Right? So in such cases, Chebyshev's inequality is good. But as we'll see, this is not the best bound that we can get. We can get much better bounds on probabilities of this particular form. All right. So any questions so far? Okay. Now, since we're talking about sequences of random variables, it also makes sense to think about convergence of sequences of random variables. You're all familiar with the concept of convergence of sequences of real numbers, right? So that's a concept that you're familiar with. But when it comes to sequences of random variables, there's no one definition of convergence. You can have multiple definitions because a sequence of random variables can converge in different ways. Remember that a random variable is not a real number. It's a function, right? It's a function from the sample space to the set of reals, satisfying a bunch of properties. So when we say convergence of random variables, we're in fact thinking about convergence of sequences of functions. Right? That's one thing to keep in mind. And when it comes to convergence of sequences of functions, this can converge in different ways. And we'll see a few different definitions, different notions of convergence in this particular class. And we'll see that these notions are in fact different. You can have convergence in one sense, but convergence not in another sense. Okay. So the first notion of convergence that I want to introduce is this convergence in probability. It's a standard term, convergence in probability. And it says that given a sequence of random variables, x1, x2, x3, and so on, we say that this converges to some other random variable x in probability if the probability that the absolute value of xn minus x greater than epsilon, this tends to 0 as n tends to infinity for every fixed epsilon greater than 0. So I fix an epsilon, some deviation from this random variable x, and I want to know if the probability that it deviates from x tends to 0 or not. Correct? So this is one notion of convergence. I'll introduce a couple of notions of convergence and then we'll see how they're different. We'll see some examples of each of these. Okay. There's a slightly stronger notion of convergence, and this is what is called convergence almost surely, or convergence with probability 1. Again, there can be a source of confusion because this is convergence in probability, this is convergence with probability 1. These are standard terms, so we have to work with these, but these are two different notions. So we say that a sequence of random variables converges to another random variable with probability 1, or almost surely, if the probability that the limit of these random variables, remember that each random variable is a function. So we are looking at a sequence of functions, and as n tends to infinity, we see if the sequence of functions converges to something or not. Maybe it converges to something. So is this sequence, is the limit equal to x or not? And this, again, there's a little bit of difference because the probability that the limit is equal to x. Right? So if this is equal to 1, then we say that x converges almost sure. This will become a little more clear once I introduce a few examples. So just to clarify, have you seen this before in your probability or random processes course? How many of you have seen these two definitions before? Or even heard of this, even if you don't remember what it is right now? Okay, I see a few half-raised hands. But okay. So that's another notion of convergence. We just treat them as definitions for now, before we understand what is really going on, what is the subtle difference between these. Right?
Can you write the same manner as convergence in probability?
What do you mean in the same manner?
With some epsilon.
Correct.
With xn minus x less than epsilon. With limit inside the probability, and that is equal to 1.
So this, in some sense, could be written as the probability that the limit as n tends to infinity mod xn minus x equal to 0 is 1. So there's a difference between this and this, and in the sense that in this case the limit is outside the probability, whereas in this case the limit is inside the probability. And we'll see why this makes a difference, why the limit inside the probability is different from the limit from outside the probability. Probably the most natural notion of convergence that you could think of is in terms of the distributions themselves, right? So each random variable xi has a corresponding distribution. It could be the CDF. So that's fxn for the nth random variable. And you see if this CDF converges to some other CDF or not. That's probably the most natural way you could think about convergence. And this is what is called convergence in distribution. The distribution of xn converges to the distribution of x. Correct? So if this happens, and we'll only demand that this convergence happens at all points where fx is continuous. if there are points of discontinuity of fx, it's okay for it to be different. Okay, but at all other points, these CDF should converge to this. As it turns out, this is one of the weakest notions of convergence. The other two definitions that I mentioned, if you have convergence in either sense, then that also implies convergence in distribution. Okay. Now, again, we're only trying to measure, when we say convergence, we're trying to measure whether a sequence of random variables is close to some other random variable or not. And the difference between these definitions essentially corresponds to how you measure closeness between two random variables. So in this sense, the closeness is in terms of the distributions, whereas in these two cases, the closeness is in something else. All right. And again, there are various different ways of measuring closeness. And one way of measuring closeness is you take the error between xn and x, correct? So in all of these, you are measuring how far xn is from x. These are random variables. So in this case, the in probability is xn close to x. Okay, but then you can also measure, let's say, the pth moment of mod xn minus x. And if this pth moment converges to 0, then we say that it converges to x in LP. Okay. All right, so these were 4 definitions. Let's try to understand what these really mean. Let's try to get some intuition for all of these. Okay, so let's take a concrete example, right? So suppose that I have a sequence of independent random variables, not identical. And suppose that the probability that xn, so xn can take only 2 values, either 0 or 1. It's a Bernoulli random variable, but the parameter varies from as you vary n. And in this case, the probability that xn is equal to 0 is 1 minus 1 by n. And the probability that xn equal to 1 is equal to 1 by n. Okay, so that's the sequence of random variables. Now, as n tends to infinity, what do you expect would happen? Yeah, if this had to converge to some random variable, what would that random variable be? So it would be a deterministic quantity, right? It's a random variable which takes the value 0 with probability 1. Okay, so let's define x to be the random variable such that probability x equal to 0 is 1. Let us see in what sense does this sequence of random variables converge to this random variable. So let's first look at convergence in distribution. Does the distribution of xn converge to the distribution of x? What is the CDF of x? Yeah, it is 0 for what x? So for x less than 0, fx of x is equal to 0. X strictly less than 0, and it's equal to 1 for x greater than or equal to 0. Okay. What about xn? What is f? What is the CDF of xn? So this is equal to 0 for x less than 0. 1 minus 1 by n for x in the range 0 to 1. And it's 1 for x greater than or equal to 1. As n tends to infinity, does fxn converge to something? So the limit as n tends to infinity, fxn of x, what is this equal to? It's 0 for x less than 0 and 1 for x greater than or equal to 0. Correct? So great. So we see that this is equal to fx of x. So we can safely conclude that xn converges to x in distribution. And we denote this by in this particular form. So I have an arrow, and on top of it I write d for distribution. Okay, so this is one way in which xn converges to x. Does it converge in probability? So in other words, if I look at the probability that mod xn minus x is greater than epsilon for any fixed epsilon. So in this case, x is just the trivial random variable which takes the value 0. So this is, what is the probability that mod xn is greater than epsilon for a fixed epsilon greater than 0? So what is the probability that mod epsilon xn greater than epsilon? It's 1 by n, correct? So this is simply, so xn can take only two values, either 0 or 1. It takes the value 0 with probability 1 minus 1 by n, and it takes a value other than 0, which is equal to 1, with probability 1 by n. So this quantity is 1 over n. And does this tend to 0 as n tends to infinity? It does. Right? So this tends to 0 as n tends to infinity. All right. So it indeed converges in this particular sense. What about, let's say, mean squared sets? So what about expectation of say mod xn minus x to the power of p? Or in other words, expectation of xn to the power of p for some p greater than or equal to 1. Again, remember, it takes, xn can take two values, 0 or 1. The probability that it's equal to 0 is 1 minus 1 by n. Probability that it is 1 is 1 over n. So what is this expectation equal to? So it's 0 to the power p into 1 minus 1 by n plus 1 to the power p times 1 by n. I'm just using the definition of expectation here. 0, so this quantity is 0. The next quantity, 1 to the power p for any p positive is for any p is equal to 1. So this is just 1 over n, and this tends to 0 as n tends to infinity. Right? So you have convergence in all these three forms, right? But as it turns out, it does not converge almost surely, right? All right, and it's not entirely obvious why this is the case, right? It requires a little more thought. So a way to think about almost sure convergence is the following. So we have a sequence of random variables. It converges almost surely if beyond a certain point, xn is close to x, always. All right. And to see why that's the case, let's sort of just run a simulation. Right. So let's look at the two examples that we know so far. One, that the example that we're working with. The other is just the empirical mean of IID random variables. Okay. So first, let's look at empirical mean of IID random variables. Let's say I take 1,000 random variables. Let me make it 5,000. And right. So let me generate IID random variables. So n. So this is going to be an average of n IID random variables, each uniformly distributed between 0 and 1. Okay. So I generate little n many random variables. I take the sum of those, and then I divide by n. Right? Okay, and I want to know what is the deviation from the mean. So what is the mean of this particular random variable? So it's each is uniformly distributed between 0 and 1. So the mean is half. So let me take the deviation from the mean. Okay, and I will just plot right. So this is what I would get. So this is the error, correct? What I notice is that, let's say I fix a particular epsilon, say epsilon equal to 0.05, right? So in the first few values of n, there's a lot of deviation. It can deviate quite a bit. But then after a certain point, it never deviates by more than, let's say, 0.2 or 0.3, right? So in this case, I've generated n random variables, correct? For each n, I've generated n IID random variables. So this is one realization. But no matter how many times I run the same thing, so every time I run, I'm going to get a new set of random variables, so a new empirical mean. But no matter how many times I run, this trend will always continue. Right? It's always going to be very close. The error is always going to be very, very close to 0. Okay. Now let's come back to the example that we were working with, right? Which is Bernoulli 1 over n. Right. So in this case, I have let me call this yn. Let me just say it's let's say less than 1 over n. Right, so for each n, I'll generate a random variable uniformly distributed between 1 and 0 and 1. What is the probability that that random variable will be less than 1 by n? 1 by n, right? So with probability 1 by n, I change the 0 to a 1. And let me do the same. Let me see. Okay, so in this case, observe that initially I have a bunch of ones, but then it becomes 0. Let me try to run this once again. There is a 1, but much later. Right? Now in this particular realization, there's a 1 really far away. Right? So what happens is that if you look at a very long sequence, you will eventually see a 1. Even though the probability of seeing a 1 for every n becomes smaller and smaller, you can't guarantee that beyond a certain point you will never see a 1. In fact, you will see a 1 with probability 1. So let us try to calculate what is the probability that you will never see a 1. What is the probability that xn is less than epsilon for all n greater than or equal to some capital N? What will this be equal to? So it's the probability that x capital N is equal to 0, x capital N plus 1 is equal to 0, x capital N plus 2 is equal to 0, and so on, right? X n plus 1 equal to 0, and so on. Like all of these, so we want to see zeros beyond a certain point. I don't care, I can make capital N as large as I want, but it should be fixed. What is the probability that this happens? Remember that each of the xi's are independent. So what will this probability be equal to? It will be 0, but yeah, so it's equal to 1 minus 1 by n times 1 minus 1 by n plus 1 times 1 minus 1 by n plus 2, and so on. But what will this essentially be equal to? It will be equal to 0, right? So in fact, with probability 1, you will see an xn, at least one xn, which is equal to 1. Correct? So if you look at the sort of horizon, you take any particular point, you are sure to see at least one xn to the right of that point where xn is equal to 1. Correct? And that is why this convergence xn does not converge to 0 almost surely. Okay, but now suppose that I had modified this just a little bit. Okay, so here I said that xn equal to 0 with probability 1 minus 1 by n. What if I made this probability xn equal to 1 to be, let's say, e to the minus n? Okay, now suppose that probability that xn equal to 1 is e to the minus n, and probability that xn equal to 0 is 1 minus e to the minus n. Would something change? The probability that xn equal to 1, it has reduced, right? So e to the minus n is less than 1 by n. So it decays much faster. But the question is, will this make a difference? It should not, and in fact it will not. You'll still get this probability to be equal to 0. All right, but now suppose I had, instead of just Bernoulli, suppose I had probability that xn equal to 1 over n with probability, let's say 1 over n. Then what would happen? What is the probability? So this is, and probability that xn equal to 0 is 1 minus 1 over n, right? So what is the probability that xn is greater than epsilon for all n greater than or equal to capital N? Is there, for a given epsilon, can I find a capital N such that this quantity is 0? So let me rephrase that. So for a given epsilon positive, can we find an n such that this quantity equals, is, let us say, less than or equal to an arbitrarily small delta? In fact, in this case, this is equal to 0. So for all, so beyond a certain point, capital N, all the values of xn are guaranteed to be within epsilon. Can I find a capital N? Yeah, it is 1 over epsilon. So for all n larger than 1 over epsilon, you know that xn is going to be less than epsilon for sure, right? So in this case, The answer is yes. And in fact, this sequence of random variables converges almost surely to X. Okay. So you see that almost sure convergence is a stronger notion of convergence than the others, right? And in fact, that is true. Now, let's see an example where you have a sequence of random variables which converges in distribution, but not in any other sense. All right. So let's take the following example where x1 is a Bernoulli half random variable. Okay. And xn is equal to x1 if n is odd, and the complement of x1, basically I flip. If it's a 0, I flip it to a 1. If it's a 1, I flip it to a 0. So it's a complement if n is even. So what does one realization of this sequence look like? So suppose that x1 is 1. What is x2? 0, right? It's the complement. And what is x3? 1. x4? 0. So effectively what I'm getting is just an alternating sequence. So does this sequence converge to anything? No, right? It's not a convergent sequence. So what is the probability that mod xn minus x is greater than epsilon? So if I take a small enough epsilon, does this quantity tend to 0 for any x? It doesn't. But what can I say about the distribution of xn? What is f xn of x? So xn takes only two values, 0 or 1. So the CDF can only take 3 different values for x less than 0, for x in 0 to 1, and x greater than 1, greater than 3. So what is the CDF for x less than 0 for any n? 0. Okay. Now, if n is odd, what is the value of the CDF for x between 0 and 1? How? Someone said 1 by 4. This is one particular n, right? So it's equal to, in fact, what is the PMF of any given xn? The Bernoulli half random variable, right? If n is odd, it's a Bernoulli half random variable. If n is even, it's still a Bernoulli half random variable, correct? Mainly because I've chosen probability of 0 to be equal to half and probability of 1 to be equal to half. So even if I flip, the distribution does not change, right? So this is equal to a half. What about x greater than or equal to 1? It is 1. So this is true for all n, right? So all the random variables have exactly the same distribution. So it indeed converges in distribution. But if I take any particular realization, this never converges. Right? So this converges only in distribution and does not converge in any other sense. All right? So these are again 4 different notions of convergence, the most commonly used notions of convergence. But all these tell you is that something happens asymptotically, correct? So essentially, if I have convergence in probability or almost surely, or in the LP sense, it says that as n tends to infinity, xn is very close. Suppose that I want to look at the deviation from the mean of some particular random variable, maybe the empirical average. Then this says that as n tends to infinity, the empirical average is close to the mean, the true mean, correct? But it doesn't really tell you what happens for finite n. How close is the empirical average to the true mean for a given value of n? What is that particular probability? And that is in fact why we will need these tail bounds. All right. So these tools of convergence in these various senses were in fact used very commonly, maybe like a few years ago, couple of decades ago, whenever you wanted to analyze sort of large system limits. You typically employed tools from these kinds of ideas to prove that in the large system limit, something nice happens. You can analyze the properties of certain large systems, be it in statistical physics or machine learning or information theory, right? So for example, in information theory, you want to know if there exist good codes that achieve a vanishing probability of error for a given particular channel, right? So you could use convergence in probability to show that there exists a sequence of codes for which the probability of error is asymptotically 0, right? Which is great. But then after all, that's only a first order result and does not tell us how good the code performs for a given n, for a given block length. Suppose I use the channel, I have given channel and I use it for n channel uses. What is the best probability of error that I can possibly achieve? What is the smallest probability of error that I can possibly achieve? And in order to get a handle on those, we use these kinds of tail bounds that we will try to derive. Right? In fact, we can prove that the probability of error decays exponentially in it. All right. So now that we've seen notions of convergence, so in general, what happens is that some of these notions are stronger than others. In fact, if a sequence of random variables converges almost surely to some random variable x, it turns out that xn also converges to x in probability. So almost sure convergence is stronger than convergence in probability. And convergence in probability is stronger than convergence in distribution. Right? And in fact, just because a sequence of random variables converges in distribution, it does not imply that it also converges in probability. Because we just saw an example where we had a sequence of random variables which converged in distribution, but not converged in probability. All right. And LP convergence is again stronger than convergence in probability, but not necessarily stronger than almost sure convergence. You could have sequences of random variables which converge almost surely, but not in LP, and sequences of random variables which converge in LP, but not almost surely. Right? But for many purposes, people treat this as the strongest notion of convergence. If you can prove that it converges almost surely, then that's a really good result. All right? And that is essentially characterized by these laws of large numbers. Right? And these were sort of standard tools which were used to analyze large system limits for various kinds of problems. So the weak law of large numbers, which you've seen before, basically says that if you have a sequence of IID random variables with a finite mean mu, then the empirical average converges in probability to mu. So the probability that 1 over n minus 1 over n summation I equal to 1 to n xi minus mu. The probability that this is greater than epsilon, this tends to 0 as n tends to infinity. Right? And we saw proof of this. Just use Chebyshev inequality. You'll see that this probability is less than or equal to sigma square divided by n epsilon square. So as for a given epsilon, as you let n to tend to infinity, this tends to 0. Right? But as I mentioned, this is not the tightest bound that you can derive. You can prove much tighter bounds for this particular probability. And that will allow us to prove something stronger, what is called the strong law of large numbers, which says that if x1, x2, x3, and so on are IID with a finite mean mu, then the sequence of empirical averages converges, in fact, almost surely to mu. Right? So for any given epsilon greater than 0 and delta greater than 0, the probability that 1 over n summation I equal to 1 to n xi minus mu. So the probability that this is greater than epsilon for any n, or let me maybe write this a little bit differently because that will help. The probability that this is less than or equal to epsilon for all n greater than or equal to capital N, this is at least 1 minus delta. So it's very close to 1. So you give your tolerance epsilon and delta. No matter how small you make this, I can always find a point beyond which with very high probability xn, this average, will be close to mu for all the samples beyond that particular point. All right, which is much stronger than saying this particular statement. So in this case, I just want this quantity to tend to 0. In this case, I want this quantity to be small, not just for individual values of n, but beyond a certain point, I want all of them to be less than epsilon. All right? And in fact, this happens for IID random variables. All right. Now, there's a different notion of convergence. And that is the central limit theorem, which says that if you have a sequence of IID random variables, remember that we looked at the average summation I equal to 1 to n of xi divided by n. Now, if I scale this by 1 by n, eventually this will converge to a number, a single number, which is equal to the mean. Right? But now if I instead scale by 1 over square root of n, this no longer converges to a number, but in fact it converges to a distribution. So this, in distribution, this converges to a Gaussian. All right. Okay, so I guess we're out of time, so let's stop here. Any questions?